It's time for us to get started again. The third session now before the coffee break that we have. So far, we've spoken about authorization predominantly facing people, right? The decisions we have to make about people, whether they're employees or customers and things like that. And we're seeing more and more things, devices, and specifically things that we need to start working with. And so now I want to bring up Peter Davis with Newstar to come and talk to us around some of the challenges and some of the questions that we have as we start looking at authorization and things. Peter.
Thank you, Jan.
This side's the steps.
But that side is closer to me. Optimization of physics. So I'm Peter Davis. I'm a distinguished engineer at Newstar. I've spent the last 15 years there. I spent a vast majority of that time doing sort of your classic identity management and access management technologies. More recently, over the course of the last 3 or 4 years, we've started doing a couple of things. Starting to build data libraries, data inventories of what we have, and subsequent policies that we could write around what those are. And those turned out to be really, really big data sets. Newstar is a data analytics company, so we gobble data up like candy. And so as a consequence, we currently have about a 2 to 3 terabyte Hadoop cluster with lots and lots of data in it, as you might imagine, from everywhere, lots of sources. And we use this to provide, after the fact, marketing analytics to our customers so that we can analyze how good an ad campaign was on television or on print or in displays, say, at Madison Square Garden. So at the point that we started to do that, we realized that with so much data, we run the risk of contaminating across the data sets and generating what was originally not PII and turning it into PII, and we needed to build a system to do that. So there are a couple other titles I have for this panel. One is, or policies for very, very small connected devices, AKA things, but I really, really, really hate the term Internet of Things and things. In fact, I'll have a slide later that explains why. Or for very, very big, large data sets. And big data, again, a term that is just a marketing term. It's not actually a technology term. And as a consequence of me not liking those, I also really don't like the word cloud. In fact, we've had the concept of cloud since back in the 70s. Right? An old boss of mine used to work at GE Information Systems, and he ran time-shared GE servers. And that was essentially outsourcing compute time to somebody else. So clouds are not new, it's just a buzzword. And then lastly, we could really talk about this as policy for linked data. So like I said, things aren't really new. We've had sensor networks, we've had smart grids, they've been around for about 15 years or so. We have fly-by-wire, which has been around also for about 15 years. We have manufacturing floors that have been automated for the better part of 2 decades. And also in energy generation, we've had a fair amount of it there. Largely, however, most of this was sensor networks. This was seeing what was going on. If something bad happened, call the tech and have them fix it. Right? It wasn't a full loop, closed loop system of automation. And so the one thing that has changed is that we are now moving to a stage in automation, systems automation, where there's no human involved anywhere in that flow. In the old sensor networks, a tech went out to fix the problem. And when he realizes when he gets to the problem that what the sensor said isn't actually what the problem was. And so there was context that the tech had that he added to the entire equation before he made a policy decision on how he's going to fix the problem. When you've had fully automated, you have to have really, really robust policies and rules and application smarts, maybe even intelligent systems, so that you can learn on the fly and figure out exactly how to solve the problem. So we'll start first in talking about sort of the thing world. So in general purpose computers like your laptop, even like your iPad or your iPhone, frankly, there's humans present, or at least at a minimum they're human managed, right? There's a server in the data center and you got sysadmins that are constantly monitoring and tinkering and fixing and optimizing. They're also always connected. And I'll talk more about this in a little bit. They also often have very steady power supplies, right? They're in your data center, they've got UPSs, they've got generator backups. Your laptop's got a 12-hour battery life now, so you don't really have to worry about running over the power outlet every 2 or 3 hours to recharge. And they also have generally good, powerful CPUs, right? They have good compute power, they can do complicated tasks. They're not really trying to be conservative with their CPU for any particular reason, like power consumption, for example. Things are a little bit different, though. They're usually very, very purpose-built, specially purpose-built. So I know I'm a temperature sensor, and my operating range is minus 20 degrees Celsius to 200 degrees Celsius. And that's my safe operating range. Or I'm an actuator, and I know that I can move something 3 centimeters forward and backward, right? I'm semi-autonomous. So again, like I said before, thing-to-thing communication is happening increasingly. And so when you have literally millions of sensors and actuators on a factory floor, you can imagine the complex policy operations that you need to actually define in order to start covering things like the fabrication plant for a GE jet engine. They have sporadic connectivity. Probably the easiest example, and then I'll go into this a little bit in greater detail in a bit, is some time ago, this was probably about 10 years ago, I was working on an agricultural automation project that was a combination of 3G radio stations and RFID readers. And the RFID readers were placed strategically around the pastures, and they were also placed strategically within the milking center where the cows are brought in twice a day to milk. And there were sensors on the pumps, so they knew how much milk Bessie gave yesterday and how much she gave today. And they can analyze the performance of Bessie and whether she needs to get a different kind of feed every day or optimize, or maybe she's not healthy, something like that. And one of the problems that the farmers always told us when we were going out sort of inventory, because we were looking at the RFID space at the time, was that I always get messy data from my field sensors because the damn 3G network keeps going down, right? All of these things were off of radios, and they're based on 3G leased circuit data-only services from the likes of Verizon and others. Sprint was another big one. So this has been a problem for a really long time. But it only, and again, that was just a sensor network. So now we have a round-trip, closed-loop system where sensors and actuators are just doing their own stuff, and all of a sudden, the sensor can't talk to the actuator or the other way around. Oops. They also have unreliable finite power. Many, many, many sensors aren't actually plugged into any kind of power grid. They have batteries. Battery life is getting better. That's great. But they still have a finite power. And they also have a sluggish CPU. So these all sort of are complete in contrast with the general purpose computer, right? So it's reasonable to believe that the policy problem for IoT is significantly different than it is for general purpose computers, which is what we do today. So let's talk a little bit more about sporadic connectivity. So when you're doing policy enforcement, you need to make them the policy enforcement point needs to have a relatively simple task. You can't ask it to compute pi, right? That's just not a useful application of that CPU. Policy decisions may require offline processing. That is to say, there's no PDP. So in a normal scenario, right, in a fully online world, you'd have PEPs, PDPs, and policy stores and policy information points, all sort of happily talking to each other, always having connectivity, never losing power. And you have HA and fully redundant and all that lovely stuff. You don't have that in a sensor, in a propane tank, for example. You have maybe redundant sensors and redundant pressure relief valves in a propane tank. But if you lose connectivity between any of those elements, the whole thing falls apart anyway. Policy information points. So David and Jerry were talking earlier about having information flow into the PEP to aid in this decision. And their examples were time and location. And so those are important factors. So everybody's seen this diagram a million times. If you haven't, let me know and I can share it to you. But this is sort of the classic, you got a PEP and a PIP and a PDP talks to a PIP and a policy store. But what happens when you have this? So I've added two things here. I've added questionable connectivity between everything but the PEP. And I've added a secondary, although it's still labeled the same name. Oops. So I now have two PDPs. And I'll tell you the story about why we have two PDPs in a minute. So this is sort of the IoT space, whereas this is kind of what we're familiar with today. So I really think that there are new tools required, things that we don't have yet. So we have billions of sensors and groups and attributes won't scale. But maybe a different concept like linked data might actually help the problem. Now, about 3 years ago, Neustar did a prototype using an RDF triple store and a data model, the management of metadata for Neustar data. And then we applied policies, and we wrote those policies as RDF statements. So you can think of it, when you're writing your policies, you're already doing this mentally, right? You say sensor 1 is the temperature sensor, and it's located in factory 1 and floor 1, et cetera, et cetera, et cetera. And I'm an HVAC tech, and I'm authorized to read the temperature off of all the sensors in factory floor 1. Now, in days of yore, we probably said, well, I just put all the factory sensors into, I'll put all the factory sensors into a group that says factory 1 sensor, temperature sensors, right? And as we heard just in the previous discussion, that RBAC, which is really what this is probably not the best way to do it. So you can say it a different way, and this is how we said it inside of the prototype that we built at Neustar. So we said sensor 1 is a IoT sensor. IoT is an invented namespace. I expect there'll be proprietary ones. I use EX here as sort of my own example. There'll be corporate ones, there'll be industry ones. But those are the places where taxonomies would get defined for things like what is a sensor. Sensor 1 location for factory 1, and then sensor 1 location for factory 2, and sensor 1 location room 231. There would be separate statements in there that say the lat long for factory 1 is XY, and the coordinates from the 0 axis of that floor for room 32 is X and Y. So now I write the policy, Peter is an HVAC tech, and IoT HVAC tech says read access to factory 1. So now we know we're talking about sensors, we know that we're talking about factory 1, and we know that we're talking about Peter as a tech. Now, this probably on the surface looks like it could be more compact, and yes, it could be. And again, the prototype that we did was not predicated on speed and performance. It was to prove a point that we thought that we saw something that was actually more optimized than doing things in traditional XACML. Now, don't get me wrong. You could encode this in a XACML statement. But that may or may not be the right way to do it. In fact, the way we did it is we encoded it in JSON LD. And I have an example of that later on. So I'll talk a little bit about sluggish CPU, then I'm going to go back to, quickly, the use case that I was talking about. So obviously, sluggish CPU is going to dictate some requirements to simplify crypto, what algorithms we're going to choose to deploy it. The ones that we've talked about mostly thus far are things like ECC. So policy decisions may require special trust processing requirements, and I'll talk about that a little bit more, but that has an impact on the amount of CPU processing that's required for the PEP to actually execute the policy. And this is kind of an odd one, and it goes back to a little bit to the connectivity problem, which is, what do you do with key revocations? Most of the IoT systems, especially in industrial today, authenticate all their sensors and actuators and command and control systems using their internal PKI. So they have certs that they issue, key pairs that they issue to sensors and actuators, and they all trust each other implicitly. At the enterprise level is basically one big policy domain. But what do you do about CRLs? If I have billions of devices, right, doing billions of OCSP calls all the time, or worse, I'm using CRLs, and my CRL list now is the size of the yellow pages of New York City, then that's just simply untenable. So there are some problems that we still haven't solved. So here's the use case. So I have this propane tank. It's got a lot of things, but among them it has a pressure relief valve and a pressure sensor. It, however, is in a tunnel. I used to use the example Lincoln Tunnel, but I figured that was bad. Now, before you say anything, yes, most of these trucks are not allowed inside of tunnels. So this is just for examples. So an alarm goes off, and the sensor and a temperature sensor says, "Oh, it's I've reached my max safety limit inside the tank." It sends a command over to the actuator who says, "Hey, dude, release your pressure. Right? You've reached a high safety limit." Some GPS data is also associated with this policy decision, because the GPS data says you're in a tunnel. So the GPS data is also sent to the PEP, and the PEP says, "Okay, I've been told I can't go off on tunnels, so and so I'm in a tunnel, so I won't vent." And there are more complicated scenarios that you could paint for this. There's lots of ways to kind of compose these different messages and where the data comes from. Some of it might come in. But notice in all of this, there's not a single PDP in sight, right? So again, using a very similar markup, and I'll speed through this because I only got about 5 minutes. Same concept. Plain English policy translates into a triples policy. And later on in our experiment, we went to NQuads because we realized that we needed to cluster statements about things, especially, not so much about policies. And so we took advantage of quads. So here are the scenarios where, that we're trying to solve for. This connection problem, the tunnel prohibits venting. EPA regulations on venting in certain areas. I didn't mention it before, but I hinted at it when I was showing you the PEPs and PDPs and PIPs, is that there was a new PDP in town. Well, in that particular case, the PDP is the EPA policy decision point. And the EPA is probably going to have their own set of policies, because they change regulations all the time. And they say, yeah, you can't do this there, right? And the truck, to stay conformant with policy, wants to get updates from the EPA PDP to their PDP. Now, they may shadow that PDP, or there may be two separate calls to the two PDPs that say, so the PEP knows to talk to both of them and says, hey, company truck PDP, is it okay for this to happen? And hey, EPA, is it okay for this to happen? There's another condition which is really important when you're thinking about the PIPs that we were talking about. So one of the PIPs happens to live inside the sensor. And the sensor says, okay, you've reached 30 PSI. That's critical. Vent. And tunnel says no. And then the pressure sensor says, okay, PSI now 40. You are now at critical. And if you don't vent in 5 minutes, the truck's going to blow up inside this tunnel. And that's kind of bad. So the EPA will undoubtedly tell you it's okay to vent in a tunnel. It's better than blowing up. I'm pretty sure they would say that. And so sort of to close up, all of this just needs to work, right? And especially in industrial applications and when you're dealing with large citizen populations surrounding all of these sensors and actuators, you got to have lots of good fail-safes. And those fail-safes are going to be written in the form of policies. So I briefly sort of scratched out thank you, web sequence diagram, for kind of the two phases of how this would work. So the first phase would be the preload token. I'm at the loading tank. I've got the tanker at the fuel station, and I'm pumping in the propane. And while that's happening, I know I have network connectivity. I probably have Wi-Fi back to the pump. And so I'm doing a client registration. I do a discover of an actuator by actuator name. So this is, where is the pressure release valve, right? Because I'll need to know that. And it'll get back a location. And then it says, okay, I need a token, because I know I might have to talk to that thing. And this is the sensor doing the work, right? So then an access token request goes in, and access token comes back. Now the access tokens that we did, I have it actually in the next slide. The access tokens we are using are actually JOTs with lots of expanded scope. And then now you're in the tunnel, and then you say, hey, open. And here's my access token. And inside the access token, the actuator says, okay, it's okay to do it here, it's okay to do it here, it's not okay in tunnels. Deny. And if it's not, then it gets back an okay. So this roughly, and I had to sort of compress it, even at 12-point font, it still took up too much real estate. But the thing, so this is basically a standard JOT. This doesn't have the header in it, obviously, and it's not encoded and signed, because otherwise it would be illegible. But you have scopes. And this is really kind of where, going back to the RDF model that I was talking about earlier, that thinking about this as a semantic problem, as a linked data problem, you actually start to build these taxonomies that industries are screaming for, frankly. Actually participate in the Industrial Internet Consortium, and I can tell you for certain that they all really would like to have the same vocabulary. Because among other things, they don't have interoperability between all their vendors and all their tooling. And you can imagine a company like GE or Boeing or even United, for that matter, that they have a vast array of technologies that they use, sourced from literally dozens, if not hundreds, of vendors. And so part of the security problem in IoT, and specifically industrial IoT, is the fact that there's essentially zero interop across systems. And consortia like IIC are trying to fix that, but it's a long road to hoe. So there are a few other applications for this. I mentioned earlier, although I didn't talk about it here, that you can use the same sort of concepts into very large data sets. Big data. You can do it in command and control systems, such as a lot of the industrial applications kind of centralize the coordination of messages across systems through a command and control system. So a master computer that sort of intercepts, and I think Eve talked about this earlier, that sort of receives all requests and responses and forwards them off to the right parties, but it does an internal policy evaluation. So your PEP is kind of inside this command and control system. Integration with risk-based authorization systems. Perfect example of this was my tunnel story when it was, let's see, I can either vent and violate EPA law or blow up. That really sounds like a risk-based authorization decision to me. There are lots of places that this work is going on. IETF, of course, they've got Core, COAP, ACE, CBOR I didn't put on here. XMPP is actually talked about a lot in IoT, especially in industrial applications. IEEE, mostly the radio interfaces, BLE and whatnot. OASIS has MQTT, OBIX, and I know Jamie's got another one to add to that list. You told me yesterday. And Contara is another place. So there's two places in particular. You heard from Eve earlier talking about UMA. And in fact, some of the stuff, even the enterprise stuff, you can apply to with UMA. And there's also a discussion group that's been around, golly, probably since I was at Contara, which is about 7 or 8 years ago, called the Identity of Things Discussion Group. And if you have questions about Contara and kind of the distinction between working groups and discussion groups, I'll let Alan answer that question. And there are many, many consortia. I did a count at one point when we were first entering the space, and there were at least 25, not standards bodies, consortia, where people just get around and talk about problems and write down, cloud level solutions to their problems without actually really solving anything. So that's it for my talk. One other thing I want to mention, and you heard me mention Contara earlier. There is some efforts underway right now to commence a new working group at Contara, specifically trying to address the policy problem domain that I just talked about, and potentially even start teasing out some taxonomy to help with at least the policy writing part, if not the vocabulary of, say, my Nest thermostat. Thank you very much. All right, Alan, I stole 4 minutes of your
Oh,
day.
that's okay. You stole 4 minutes of our coffee time, because I think we have a little bit of a break now and start up again at 1:15, I believe.